Welcome to this video, the second one in the series for reliability. In this video we will start from components in parallel. If you want to know the introduction, why we use exponential distribution and the systems in series, please watch video number 1. In the case in which for these reliability block diagrams we have concurrent components in parallel, what needs to happen is that all of them would have to fail before the system fails, at least in that subsystem of parallel components. So the easiest way to compute this is the joint probability of the failure of all of them. The probability of failing is 1 minus the reliability, and what we need to do is the joint probability of all of them failing, and then subtract 1 minus that joint probability, and that will be the reliability of the system. The mean time to failure of the system can also be computed relatively easy when we have these components, and we have 1 minus lambda times 1 plus 1 over 2 plus 1 over 3 and so on, all the way plus 1 over n, depending on the number of parallel systems that we have. Here the word concurrent is not necessarily what you find in the literature, but it's a way to describe that all of them are working simultaneously. There is not the process of waiting for one to the other to fail. The number of failures could be just any number except as long as there is one left. But all of them are working simultaneously at the beginning. Here we have an example. And the question is, compute the reliability of a system with two identical components in parallel after 3,250 hours. The mean time to failure are 1,500 hours for both of them. Compute the mean time to failure for the system. So here we can compute the reliability of each one of the components on their own as e to the minus lambda t. In this case, e to the negative 3,250 over 1,500, and that yields 11.45%. Then we compute the reliability of the system as a whole, and for that we estimate the joint probability of both of the system failing, and that is each one of them failing is 1 minus the reliability of each one of the components. So from the joint probability of both failing, we subtract that quantity from 1, and the final reliability of the system is 21.6%. The mean time to failure, if the mean time to failure is 1,500, this yields 1 plus 1.5, that is 2,250 hours. Notice that in this case, the mean time to failure originally was 1,500, but by virtue of having a backup on the second one being in parallel, the mean time to failure increases to 2,250, and therefore increasing the reliability of the system by having the components in parallel. When we have systems in parallel, we could also have a different arrangement or architecture in which it may not be sufficient to have only one, but we need at least a certain number of these components working in order for the system to perform as a system in the way that we want it. So if we denote x as the minimum number of components that are needed to operate properly in order for the system to operate properly, and n is the initial number of components available in the structure of these parallel components, and r sub I is the reliability of the component I, then the reliability of the system can be computed as the binomial distribution. Now this is a rather unusual way to use the binomial distribution, because what we are looking for is that we want to find that there are not enough failures to make the system collapse. So we count the number of failures, and here the number of failures allowed is n minus x. That's how many failures we could have. We could have 0 failures or 1 failure and so on, as just as that number does not exceed n minus x. It can be n minus x, but cannot exceed n minus x. And the number of combinations would be that n selected out of all these different components that are available originally. And the probability that is of interest is the probability of failing. So we use 1 minus the reliability of each one of these components that are assumed to be the same. And then the complement of that is needed in the binomial distribution is, of course, the reliability, and that is to the power of n minus 1. So we are actually counting the probability of having less than or equal to the number necessary for the system to remain in operation after we count the probabilities of these failing components to fail up to that number that will allow us to remain in operation. So this is the example of the binomial case where parallel systems. The question reads, compute the reliability of a system that has already 1,000 hours of operation and has 6 components in parallel. The requirement to operate the system is to have at least 4 components to operate. The components have to have a constant mean time to failure of 4,200 hours with exponential reliability. The steps are, first, to compute the reliability of each one of the components. Since they are all the same, the reliability of these components after 1,000 hours is e to the negative 1,000 over 4,200, and that number is 78.81%. Once we have that number, we can compute the reliability of the system as a binomial for the cumulative cases when n equals 6, because we have 6 components, and the number of interest will be 2, because we could have 0 failures, 1 failure, or 2 failures, and we would still have 4 operating components, enough to for the system to remain operational. So the numbers of interest, the number of successes in a binomial distribution in this case would be 2, although the concept of success is actually to fail. And the probability of failure is 1 minus the reliability of each one of these components, and the complement is the reliability times n minus 2 to the power n minus 1. So disclosing these numbers one by one, we have combinations of selecting 0 out of 6 times the probability of failing to the power of 0 times the probability of the reliability to the power of 6 plus the combination of selecting 1 out of 6, that is 1 failing, and times the probability of failure to the 1 times the reliability to the 5, and finally selecting 2 out of 6 with the probability of failure twice, that is failure, the probability of failure to the power of 2, and the reliability to the power of 6 minus 2, 4. And when we do the computations on that are disclosed on this screen, and you can verify it on your own, the reliability of the system is 88.6. We have yet another behavior for the cases when the parallel components are the structure in the system. And that is, instead of being concurrent, instead of all working together, only one at a time is working and the other are holding on in standby. In that case, what we need to use is the Poisson distribution that counts in association with events that have separation of events in exponential way. We count the number of events that have to happen in such a way that if you have, say, for instance, 5 components, as long as you have 4 or fewer failures, you still will have at least one to keep working. So that's why we have the probability of the Poisson distribution, the cumulative distribution of Poisson, as a model to use. Typically in the Poisson distribution, we only have the parameter lambda, but here the average depends on the number of hours of operation. That is, the expected number of failures is the failure rate times the number of hours of operation. That's why in this case the adjusted Poisson distribution that we use is not only using lambda, it's using lambda times t, because that will be for the number of hours of operation, the expected number of failures in the system. So with that, we can make the computations of an example. Here is a standby behavior in parallel systems. The question is compute the reliability of a system with 4 parallel components with a standby behavior. The mean time to failure is 1000, and we are interested in the reliability of the system after 2300 hours. So we use the cumulative for Poisson, and the number of failures that it's of interest would be 0, 1, 2, and 3, because we have 4 components, and as long as we don't fail 4, then we will have a chance for the equipment to remain operational. Lambda times t in this case is 2.3, because what we have is that the number of hours is 2300, and the mean time to failure is 1000 hours, and that ratio is 2.3. So we compute the reliability of the system as a cumulative Poisson distribution for 0, 1, 2, and 3, and that number yields 79.93%. For the case of more complex systems, the methodology of using the reliability block diagrams is very powerful, because we can depict a lot of the complexity on components and how they are interacting among themselves. So if you have part of the system being parallel and part of the system being in series, or components that together work in parallel but respect to others work as in series, all that can be depicted. In this example, I'm working that situation with items in series, but also items in parallel, in concurrent parallel, and I'm not including in this case the use of binomial, and I'm not including in this case the situation with the standby components, but all of those could be included in the system depending on how the behavior of each one of the components in the system is. In this example, we are solving a case in which we have first 2 A's, A1 and A2, that work together in parallel. It's a concurrent parallel situation. And then B1 and B2 have a similar concurrent parallel situation, but the A's with respect to the B's work in series. Both have to happen at least. In other words, with this diagram, what we are depicting is that we need at least one A and at least one B to be able to work. Fortunately, we have 2 A's. We have some level of backup. It is not as good as the standby behavior, but it's better than nothing. And it's not a binomial. It has to be at least 1. So the computations for this example are, first, we need to know the mean time to failure for each one of these components, and the mean time to failure respectively for A1, A2, B1, and B2 are 1,000, 1,500, 2,000, and 2,500 hours. The question is to compute the reliability of the system when the system has worked for 400 hours. So first what we do is we compute the reliability of each one of the components when they have worked 400 hours. Here the only change from one component to the other is the mean time to failure or the failure rate, and we can relatively easily compute the reliability of each one of the components. Now, before we can do the series, we need to calculate the reliability of the pair A1, A2 working together in parallel. So we do that, and we obtain the value of 92.28% for A's, and the reliability of B's is 97.31. And that is what we would expect, because when we have parallel systems, the overall parallel should be better than the independent component reliabilities. Now that we have the reliability of the pairs that are working in parallel, we can compute the reliability of the system for these two components that are working in series as the joint probability of their corresponding reliabilities. And when we replace the numbers with the reliabilities of each one of the sub-assemblies, what we obtain is 89.098% of reliability. So this is the example for the combination of these networks, and I hope you find it useful, and let me know what you think.